Breaking! Hidden flood explodes through Greenland ice sheet. In an extremely surprising event, a hidden lake in Greenland blasts through massive ice blocks. July 30th, 2025, 3-minute read. Typically, water follows the path of least resistance, flowing downward. But in a bizarre turn of events, a torrent of water under Greenland's ice sheet surged upward, carving out a space nearly double the size of New York Central Park. This unexpected phenomenon, where water defied gravity, has left scientists scratching their heads. By Stephanie Pappas, edited by Jenna Briner. In 2014, a subglacial flood in Greenland erupted through tens of meters of ice, lifting blocks the size of 5-story buildings and clearing an area nearly twice the size of Central Park in New York City. This peculiar event, where water flowed upward instead of along the base of Greenland's ice sheet, was described as extremely surprising by Winnie Chu, an assistant professor of geophysics at the Georgia Institute of Technology. Chu, who was not involved in the study but has expertise in Greenland's ice, noted that such an occurrence requires extremely unique conditions. The flood, which went unnoticed on the ground near Harder Glacier in far northern Greenland, was discovered a decade later by Mal Macmillan, a professor of Earth observation at Lancaster University in England, and his team. They stumbled upon the flood while analysing satellite imagery for signs of lakes beneath the ice. These subglacial lakes are crucial as they influence the overall water cycle and ice movement in Greenland. They typically form from surface meltwater that drains down and becomes trapped between the ice and the bedrock. Occasionally, they rapidly empty, sending water flowing between the ice and rock, sometimes to the sea and sometimes under glaciers, where they act as lubricants, accelerating glacier flow. Accounting for the impact of these small lakes in models of the Greenland ice sheet has been challenging due to their size. However, improved imagery has allowed researchers to detect upwellings or depressions in the ice that indicate a subglacial lake is filling or draining. When examining historical data near Harder Glacier, the study's team noticed a 2-square-kilometre area of ice that had collapsed into an 85-metre deep sinkhole. Further investigation revealed a fracture zone downstream, which was unexpected. Beyond the fracture zone, a 6-square-kilometre area of smooth ice was found, indicating a massive deluge. The researchers realized that the collapsed area was a subglacial lake that had rapidly drained. However, about a kilometre downstream, the water encountered an obstacle. Instead of flowing down, it pushed up, creating an upheaval of ice blocks and crevasses, and a dramatic gush of 90 million cubic meters of water, equivalent to the amount of water that goes over Niagara Falls in 9 hours. This all occurred within about 10 days. The water then drained back under the ice sheet and may have ended up beneath Harder Glacier, which coincidentally experienced a large calving event during the same 10-day period. The glacier also saw unusual changes in its flow rate that summer, suggesting that the flood had an impact on its dynamics. According to Robin Bell, a professor of marine and polar geophysics at Columbia University's Lamont Doherty Earth Observatory, this event is another piece in the puzzle of understanding how large ice masses on our planet work. The next question is how this puzzle piece fits into the broader narrative of Greenland's rapid warming. Macmillan, the lead researcher, stated, "We need to understand whether this has happened on other occasions." Supporting science journalism. If you're enjoying this article, consider supporting our award-winning journalism by subscribing. By purchasing a subscription, you are helping to ensure the future of impactful stories about the discoveries and ideas shaping our world today. Massive hidden flood breaks through Greenland ice sheet. Imagine a force so powerful, it can shatter through almost 300 feet of solid ice. That's exactly what happened in Greenland in 2014. when 24 billion gallons of meltwater burst through the ice sheet, marking the first time such an event has been recorded. This unprecedented flood, originating from a subglacial lake, has stunned scientists. The force of the water was so intense that it fractured the ice, leaving behind ice blocks as tall as 82 feet, and scoured an area twice the size of New York's Central Park. The implications of this discovery are profound. Scientists previously believed that meltwater flowed from the surface to the base and then out to the sea. However, this event challenges those assumptions, suggesting that subglacial lakes can play a significant role in the ice sheet's hydrological system. What we've learned from this study is that ice sheets can respond to extreme meltwater inputs in ways we hadn't anticipated. Co-author Amber Leeson, also from Lancaster University, noted, "The Greenland ice sheet, one of only 2 permanent ice sheets on Earth, covers an area nearly 3 times the size of Texas. It loses an estimated 33 million tons of ice per hour, contributing significantly to global sea level rise." Understanding the behavior of subglacial lakes and their potential to release vast amounts of water could be crucial for predicting the future stability of the ice sheet. This groundbreaking research, published in the journal Nature Geoscience, highlights the need for further investigation into the hidden processes beneath the ice. And this is the part most people miss: the fact that we're just scratching the surface of what lies beneath the ice. Bowling emphasized. But here's where it gets controversial. Some scientists argue that these subglacial floods could accelerate the melting process, potentially leading to faster ice loss than current models predict. What do you think? Should we be more concerned about the hidden threats beneath the ice, or are current models sufficient? Share your thoughts in the comments below. The impact of subglacial floods on Greenland's ice sheet. Greenland's ice sheet has made headlines for its dramatic loss of ice over the past 30 years, shedding roughly 169 billion tons annually. This relentless melting has contributed approximately 14 millimeters to global sea level rise, and that number keeps climbing as temperatures in the Arctic region continue to escalate. About half of this ice mass reduction results directly from surface processes, mainly accelerated melting and runoff from the ice's surface, driven primarily by warming temperatures, which promote increased surface melting and the formation of runoff channels. With Arctic temperatures projected to rise even further, the extent and severity of surface melting on Greenland are expected to intensify, leading to more significant ice loss. This melting not only reduces Greenland's overall ice mass, but also results in increased accumulation of liquid water on, within, and underneath the ice sheet, which can influence the sheet's stability and movement. Understanding how meltwater moves from its point of origin inside the ice sheet into the ocean is central to predicting Greenland's future impact on sea levels and broader Arctic systems. It is well established that surface meltwater can carve pathways through moulins and crevasses, channeling water down to the bedrock beneath the ice. Studies, especially in southwestern Greenland, have shown that these subglacial hydrological systems respond swiftly to water influxes, with the flow of water beneath the ice varying over time and exerting a direct influence on ice sheet movement dynamics. Key to this understanding is determining whether water drains continuously or episodically, and through which routes: surface channels, end-glacial pathways, or subglacial conduits, and whether water is temporarily stored during its journey. These factors are critically important because they influence ice movement, internal thermodynamics, interactions with the ocean, circulation within fjords, and the transfer of nutrients and sediments into the ocean. A particularly intriguing aspect is Greenland's network of subglacial lakes, hidden reservoirs of water beneath the ice sheet that have only recently been identified and remain poorly understood. These lakes are mostly fed by surface meltwater that reaches the base of the ice and can store large volumes of water. When they drain suddenly, they can release enormous quantities of water into the subglacial drainage system, potentially deforming the local ice structure and affecting the dynamics of surrounding ice. However, direct observations of these drainage events are rare, and scientists still struggle with understanding exactly what triggers them and what their consequences are. A critical unknown is the thermal state of the ice underneath, specifically whether the base is frozen or temperate, which governs how water distributes and moves beneath the ice. As meltwater runoff increases, especially during the 21st century, there's likely to be more frequent and larger drainage events from these lakes. But how such events influence the overall stability of Greenland's ice is still uncertain. Recent research has focused on a particularly dramatic and destructive mode of drainage. Using high-resolution data from satellite imagery and digital elevation models, scientists identified and monitored a previously unknown subglacial lake in northern Greenland, near the Harder Glacier. During a 10-day window in summer 2014, the ice surface over a 2 square kilometer area abruptly dropped by about 85 meters, forming a deep depression, an event that suggests a sudden release of water from beneath the ice. Prior to this collapse, the surface had actually been rising, forming a dome that gradually increased in height, indicating the presence of an active subglacial lake. After the lake drained, the surface began to rise again, but then subsided by roughly 10 meters between 2017 and 2019. These dynamic behaviors match the typical signs of active subglacial water reservoirs connected to large drainage events. Estimations based on the volume of the newly formed surface feature suggest that around 90 million cubic meters of water was discharged during this period. The water likely came from locally sourced surface meltwater, with over 99% originating from the immediate catchment area, and water drained at an estimated average rate of 100 cubic meters per second. This rate far surpasses typical meltwater flows, marking it as one of the largest known drainage events beneath the Greenland ice sheet to date. Such a huge flux likely caused significant perturbations in the subglacial system, with potential consequences for ice movement. Traditionally, the flow of water beneath the ice sheet is thought to follow a unidirectional path driven by hydraulic potential gradients from the surface down to the bed and ultimately into the ocean. But the 2014 event revealed a different mechanism. Evidence suggests that floodwaters broke through the ice at a fracture zone, an area of intense crevicing and uplift, about 1 kilometer downstream of the lake. This fracture zone shows signs of extensive surface cracking and uplifted blocks, implying that water managed to reach the surface by breaking through the ice via hydrofracture, a process where water pressure and cracks cause the ice to fracture upwards, rather than flowing solely along the bed. Analysis of the history suggests that such a surface outburst was unprecedented. Previous signatures of lake drainage, visible in satellite records from as far back as 1985, did not produce surface fractures or the same level of upheaval. The downstream effects of this lake outburst were also notable. Evidence indicates that the floodwater, after bursting upward, flowed across the surface and then re-entered the ice sheet's internal channels, traveling beneath the glacier. This process likely contributed to a significant calving event at the glacier's terminus, one of the largest in over 3 decades, potentially driven or amplified by the sudden influx of water, causing stress and melting at the glacier front. Data on ice velocity and surface changes suggest that immediately after the 2014 flood, the glacier experienced a rapid deceleration, its speed dropping by about 80 meters per year, significantly more than usual. indicating that the flooding may have temporarily increased the efficiency of subglacial drainage, reducing basal water pressure and altering movement. Such a rapid change demonstrates that even fast-flowing, marine-terminating glaciers are susceptible to sudden internal hydrological. The basal temperatures remained well below freezing, implying that the lake was probably sealed beneath a cold, frozen bed, with water reaching the surface through hydrofracture rather than basal melting. An alternative scenario hypothesizes a thermally temperate bed with basal melting, but the data suggests that the most plausible explanation is a hydrofracture driven by external water pressure, not melting from below. Further analysis of the conditions needed to initiate the lake's drainage supports the idea that a sudden increase in shear stress caused by the expanding subglacial lake overcame the ice's strength, causing upward fracture propagation. The process is complex and likely involves a transition from basal shear stresses to tensile stresses within the ice column, prompting a crack to grow upwards and ultimately reach the surface. This kind of hydrofracture-driven drainage is distinct from the classic model of meltwater flowing along a warm, forward bed, and suggests that in regions where the bed remains frozen or its thermal state uncertain, water can be stored and then rapidly released through a destructive hydrofracture process. This discovery indicates a fundamental shift in how scientists understand subglacial hydrology. Conventional models emphasize a mostly warm bed mechanism where meltwater flows freely and persistently at the base of the ice. But here, evidence suggests that large volumes of surface meltwater can be stored in a cold-based environment and then suddenly released through a hydrofracture, capable of damaging the ice structure and influencing glacier flux. With climate warming expected to increase surface melt and possibly expand cold-based areas inland, the potential for such destructive surface-reaching drainage events may become more common, posing new challenges for predicting ice sheet stability. In sum, this study presents compelling evidence that a subglacial lake can rapidly drain upwards, piercing the ice through hydrofracture, even in a largely frozen environment. The event involved primarily surface meltwater, which accumulated and then suddenly burst through a fracture zone, influencing the nearby glacier's movement and stability in profound ways. These findings question the traditional view of meltwater flow as stream-like, always directed downward, and open the door for new questions. How widespread is this phenomenon? Could similar processes be happening elsewhere in Greenland and Antarctica? And what does it mean for the future of ice sheet stability as our climate continues to warm?